Thank you everyone for coming. It's nice to see that so many of you have come here and listen to. As you said, I'm from Waals Cook, and we have a lot of interesting quantum projects in different directions. But I'm here to talk about my research, which is miniaturizing quantum entangled sources. So to begin, a little bit of motivation. Why do we want to miniaturize these quantum sources? Is especially because this is quite established already. Like quantum entangled photons, you can generate them, and it's already known for like 20 years. But especially what are the research interest now is we want to incorporate them into some like smaller size like chip quantum chip computing. Then the space becomes a problem actually, and you will need something which is more compact, and that's actually what we are trying to do. So trying to develop different ways of generating these quantum entangled photons in a very compact space. And to begin with some outline when I'm going to talk, we're going to start with some like very basic background. Probably most of you already very familiar with this. Then I'm going to review some of the like current work, what other people have also done in this miniaturized photon pair generation. And then I'm going to show our work, and I'm also going to talk about what are the directions, what we're interested, especially in the future. We started roughly 1 year ago, so there's some results, but there's also things we are interested to study in the future. We are working with nonlinear optics, so especially we are interested in materials which have a high to second order susceptibility. And this is important because this will basically dictate whatever is the generated light nonlinear processes that we can get. And in the quantum regime, what we are especially interested is SPDC down conversion. So in this like very classic or the like bulk regime, you would have non-photons splitting into a signal idler, and the probability of this is dictated by phase matching and energy conservation. So basically, this is how you in the bulk optics version you would like kind of tailor your sources, and you can like modify the phase matching to produce different kind of emission cones. And where if you want to generate entanglement in this way, you would have two very classic ways, which are like very established already. So you would have type 2 entanglement. So you would have the signal idler generated in a orthogonal polarizations. When we talk about polarization entanglement, especially, and then in this, when these two cones overlap and plot the photons here, you would have the polarization entanglement. And then the other way is type 1 phase matching, or doing with type 1 phase matching. So you would have two crystals which are orthogonal to each other, and then because you can't know from which crystal you generated the photon from. You collect the photons wherever in the ring, you would actually have a polarization entanglement, and yeah, they are generated in a slightly different state. There's two ways, optical ways of generating the polarization entangled photons, and yeah, general classical characteristics. So you would collect the photons with two detectors, and depending, this is a general characteristics of polarization entanglement. So depending, you set the one arm polarization in the one arm will be constant, and then when you measure the coincidence counts, it's a function of the polarization in the other arm. Depending on the projection in the one arm, you would have a phase with this, and yeah. So and then if you want to have the most information about your quantum state, you would perform quantum tomography. So you would project the photons in their different states, and actually you can calculate the density matrix, and this will give you all the information about the quantum state that you have generated. And now that we move on, so this is already the basic information. So if we move on to the photon generation, so it's can also be generated as in bulk optics with the nonlinear, with the down conversion, and some of the characteristics are similar. So you would have a high tube material, but actually some of the characteristics are also very different. So in the case when you generate the photons in like a very thin interaction length, you would actually have a less importance for the phase matching condition, because if your interaction length is less than the coherence length, then all your photons will be generated in phase regardless if you care about the phase matching. And actually this results to a very broad emission pattern and a very broad spectrum emission. So if you compare, this is like a general, like a phase matching from the bulk crystal. So it's very strictly constrained depending on the properties of the crystal. But in the case when you generate the photons from a very thin crystal, you would have a much more freedom, actually, both emission angle, the emission wavelength, and of course everything comes with a downside. So you cannot, it's not that easy. Actually the biggest downfall when you want to reduce the interaction length, obviously you will also have like a low emission rate, and actually like very low emission rates. So most of these current studies, the emission rates or the photon pair generation rates of these samples usually are way lower than what would be needed, for example, for like an actual computation needs, or in any kind of like actual like application needs. And then of course we still need to produce some more ways to generate entangled photons, which I will talk a little bit more in a bit. So especially in this path research, they have, for example, used meta surfaces. So this is one good way of like tailoring your emission from these thin samples, because as I said, you have the basic constraint is that you can have a very broad angular and spectral emission. So you can actually use that as a basis, and then you can have some kind of resonances, for example, resonant meta surfaces. So you can, for example, tune these emission depending on what kind of resonances you have designed for your meta surface. And also same group, they have shown that they can also show like directional emission. They study that actually like this whole product like a bidirectional emission is actually very efficient also from this kind of meta surface. And in the same way with the meta surface emission, you can tune the angular emission. So this one, they actually, what they did was they generated like a angular propagating modes in this meta surface, and with this they can actually tailor how the photons are, which angle the photons are emitted, and this way they can actually show that they can show like continuous variable entanglement, this kind of meta surface thin film source. And similarly, people have shown polarization entanglement. So in this case, they actually used like a very thin gallium phosphide layer, and they were able to show a polarization entangled photons from this sample. But actually, even in this case, because the sample, the nonlinear coefficient of this material is actually still on the same same range as what you would have with bulk crystals. So when you make it a very thin, you would actually like have a extremely low emission rates. And I think these coincidences here, they managed to get like with I don't remember the exact power how much they used, but it was on the power regime. So they had to use a lot of powers to even this kind of emission rates. And on the other hand, the tunability. So you would have you would have a very broad difference in there. So what they showed, they can like switch between non-entangled and entangled state. But actually, the non-entangled state is still like much brighter than the entangled state. And more recently, because now like what is of interest is to find like maybe better materials which should have higher nonlinear coefficient, especially to increase this generation rates. So 1.5 years ago, they showed this one. So MbOCl, and then this is an interesting material in the sense that it has a extremely high nonlinear coefficient. So it's on the same level or maybe a bit higher than transition metal dichalcogenides. And the advantage of this material is that it has a extremely low interlayer coupling. So what that means is you can stack different layers together and the layers don't interact with each other. So for example, with the transition metal dichalcogenides, you would have like a transition between the bulk properties and the monolayer properties. With this one, for example, if the single layer interaction length is not enough to produce photon pairs or down conversion, but when you like just stacked enough layers together, then you would still have like subwavelength range, but you would have enough interaction length already to actually produce photon pairs. So what they did in this paper, they show that it's actually quite efficient in photon pair generation, and it scales well with the thickness. And then on the other, which is even more recent, they also used transition metal dichalcogenides, so MOS2. In this case, what they did was because they fabricated in the 3R phase. So because generally the common 2H phase have a cancelling nonlinear susceptibility when you stack the layers together. But with this one, they can actually have like a thicker, so the thickness of the sample is 300 nanometers. And in this case, they will still have like a switching with the other properties. So, but in this case, it's actually beneficial because the monolayer MOS2 would have a quite high fluorescence, but once you stack them together, you will actually quench the fluorescence. So the thicker samples, the band gap shifts towards indirect, if I'm not incorrect. Yeah, and in this case, they also show photon pair generation, but for this one, they actually this one they show like there is a as I talked, it's a very broad spectrum, but the photon pair generation is actually extremely low for the 3R MOS2, even in the case of having like the 300 nanometer sample. So if you compare these two materials, actually MbOCl has a higher photon pair generation rate. But the advantage of the MOS2 is that the photon pairs that are generated, they are directly entangled, so the nonlinear the material is much better. And now I move on to our work. So since the MbOCl is the photon pairs that are generated, they are in the generated just the two photon pairs are the same polarization as the pump, so they are not polarization entangled, and therefore like this is not as of like for most of things it will be interesting to have the photon pairs from the entangled state. So what our project, what we try to do is to generate this in the entangled photons for M2. And before I go there, I'll just show first like our experimental setup. So we have this very basic for photon barrier detection. So we have a laser pump. We some polarization optics to make the polarization linear here. Then with a dichroic mirror, we collect in our back reflection geometry. We collect the photon pairs that are generated here at the sample. And then with the beam splitter, we can measure the coincidences. And with our setup, we have all the polarization optics to kind of fully characterize the quantum state. And here is a typical MBOCL flake. So this is like the one which we started with. So it's just a quite thick slab MBOCL. So in this case, the thickness would be around 1 micrometer. From these kind of samples, we can see that we actually measure the coincidences. So this is just the basic down conversion from like a big slab of MBOCL. So when we measure power dependent, the coincidences show this characteristic of the signal to noise ratio to kind of decreasing the increased pump power. And then we have a full polarization characterization. So we measure the coincidence counts as a function of the pump polarization. Then the collection arm, the polarization is set to like be relative to the pump. So in this case, along the pump, both perpendicular, and then the two where the polarizations in the detector arms are like perpendicular to each other. So as we can see, this is very similar to the one which was in the paper. It was very brief, but we didn't see, but the same as the second harmonic generation. So this follows a similar pattern than the second harmonic generation, the material. So actually most of the SPDC photons are generated along the pump polarization. So as I said already, it's not entangled. So what we wanted to do for our project, so our plan was to combine two flakes together, and when you pump these two flakes with a pump that's partially along the perpendicular crystal axis, you would get like photons from both flakes same time. And then if everything is well balanced, basically you would have the similar amount of photons from all flakes. Then you would have polarization entangled state from this kind of 2D material heterostructure. This actually follows. This is the idea comes from the type 1 bulk crystal polarization entangled scheme. And so what we did, so first we fabricated the sample, and so we put a slab of MBOCL on top of another slab of MBOCL, and how we can tell that they are perpendicular to each other. So we measure this same polarization dependent coincidence count, and these are both measured individually. So not from the stack flake, but there's a small piece of the top flake, like here. I'll set the picture where we can like measure so like individually. So we can see that from these two flakes, SPDC photons are generated perpendicular to each other. So potentially in the middle we could have the polarization entangled state. But for this one, because in the initial attempt, it's also a bit about the setup, because now actually our setup is much more sensitive, so we were able to make the setup better aligned. So we are able to measure the photon pairs from much thinner flakes. But this is done maybe like 8 months, like last year, end of last year. So the top flake is actually quite thin, and the reason is actually that is also quite anisotropic. So this is kind of a problem we had to work around. So the other part of the pump, which would be like we have the polarization for the top flake and then from the bottom flake. So the polarization for this component, the penetration depth is actually not that much. So for the generated photons at 800, the MBOCL is quite transparent, but for the pump is kind of something we had to work around with. So we had to fabricate this top flake in a quite thin manner, or like we had to make it thin enough for the pump to be able to reach the bottom flake. So I think for the next attempt we will actually be able to balance for this better, but in this first sample, the thickness is actually quite disproportionate. Yeah. So then this is just a similar data, just but in a time domain. So similarly, we can measure from the individual flakes. Now it's just in these 2 measurements, we just align the pump along the corresponding crystal axis, and then we just measure using this same coordinate system. So we actually define the top flake axis to be H, and then bottom flake axis to be B as in vertical. So yeah, we just show that most of the photon pairs each flake are generated in the perpendicular directions when the pump is along the corresponding crystal axis. And then we move on to the pumping from the stacked area. So in this case, what you would see first is that these two components. So the H, we will start from measuring in the H3 basis, and you would not see these to be balanced because it depends on the pump angle. And then we would first measure these two components and tune the pump angle. Then we can see that these two are well balanced. And so this is actually quite similar to the type 1, how we align the type 1 entangled source. And then after that, we can measure after the pump is aligned such that HH and BV equal. You can still see that there's the H3 and BH are quite low. Then we could measure in alternate basis to see that actually the generated photon pairs do exhibit some coherence between each other. So basically they're indistinguishable, and there's polarization entanglement between them. And we can also do this same thing. So the earlier figures that I showed. So we fix one of the arms to be either E or A, and then we measure polarization dependent coincidence counts on the other arm. So we would actually see this 90-degree shift when the one arm that is fixed in the one position will be shift by 90 degrees. So it shows that the photons that we're measuring exhibit polarization entanglement. And lastly, we also measure the full quantum state tomography for this sample. So we can actually see that even in this one, the density matrix that we get does correspond to the entangled state, which we expect. So HH plus BB. So this this is what we did for this one. And now for this one we are still continuing. So we want to, what we are doing now on this project, we want to kind of measure and see if we can measure, like we can fabricate flakes with different thickness, and we can see some kind of difference in the fidelity, trying to distinguish what kind of factors that might be affecting that. And then in general we are also like what we are studying, so we measure all kind of different thin film samples. So we are also interested in fabricating different structures. I didn't have the slide for this one, but so we have, for example, metallic or dielectric structures, and then using the resonance of those, we can actually enhance the quantum field, and this way we can increase the photon pair generation rates. So I think this is something all the groups that are in this field are also mostly interested, because that's one of the things that needs to be kind of addressed, is the low photon pair generation rates, because otherwise in the current realizations are still the regime that is not enough. They are not efficient enough. It's kind of a challenge because you have to work with such a low interaction length. So we are actually also studying the 3R too currently. We have a lot of projects going on. But that's pretty much it actually.